Hello, and welcome to Physics 350, Classical Electrodynamics, fall of 2019. Welcome to the class. And this lecture will be an introduction to the class and a brief review of electricity and magnetism at the level of Physics 202, which you all have taken. And also covering chapter 1.1 of the textbook, which is a review of vector algebra, dot product and cross product, and that sort of thing. So, an overview of the class. We're going to do this class a little bit differently than traditional lecture classes. We're going to, you may have experienced this in a math class, but if not, we're going to do a flipped classroom. So before each class, you're going to watch the lecture beforehand, which I'll have pre-recorded. And then when you come to class, and you can watch the lecture or parts of it that are confusing several times and even bring questions to class. And you will be working problems in class, in groups during class. And those groups will rotate during the semester. I know you like working with your friends or people you have known beforehand, but I think you'll find that working with people with different styles, while it might be unfamiliar or intimidating to work with someone you don't know at first, you'll eventually find it to be beneficial. And there's evidence that this flipped classroom leads to a stronger grasp of the material. Rather than listening to a lecturer like me talk about something somewhat more passively, if you listen to the lecture beforehand and then come in and actively attempt during class to work problems, you can make greater gains in terms of your understanding of the material together. There will also be problem sets in addition to the work problems during class. So this class is going to be a deeper study of electricity and magnetism. What I mean by a deeper study is it's going to lead to Maxwell's famous equations and his four famous equations, the Maxwell equations, and also to group projects, which you'll be doing at the end of the semester. After we finish Maxwell's equations, you'll have the chance to extend some aspect of the course in groups of 4 or 5 in an interesting direction. Okay, so you can explore some aspect of electricity or magnetism as in groups. We'll be using vector fields and some new operations. So vector fields, you already know, are familiar with examples of vector fields. There's the electric field and magnetic field, which are vector fields because there's a vector at each point in space. And so that's an example of a vector field. But we haven't done any calculus or taken derivatives of vector fields yet. And so we're going to be learning what's called vector calculus, and that is going to involve the gradient, which is this upside down, usually written either grad for gradient or this upside down triangle, div for divergence, or curl for curl. So there's 3 different types of operations, basic operations in vector calculus: the gradient, the divergence, and the curl. Okay, so let's go over some concepts from electricity and magnetism in Physics 202. We're not going to cover everything in Physics 202, but there's Coulomb's law. Okay, and in just a minute I'll go over some of these equations so you can just be reminded of these equations. But just generally, there's Coulomb's law for the force between charges. There's electric flux and Gauss's law. Okay, so electric flux being the amount of electric field that radiates through a certain surface, and Gauss's law, relating that to the amount of charge inside of that surface. There's electric potential, also known as voltage. There's the magnetic field, the thing which makes a compass point in the direction that it tends to point, and magnetic force, which makes magnets stick to refrigerators or compass needles line up with the magnetic field lines. And a more subtle or more slightly more challenging aspect of magnetic field and magnetic force were the Biot-Savart law, or in French, the Biot-Savart law. We'll use the English pronunciation, the Biot-Savart law, and Ampere's law, also known as Ampere's line integral law, again, which I'll show you the equations for those in a second, but they were ways that we could calculate the magnetic field. Then there's Gauss's law for magnetism, which turns out to be especially simple, as I'll remind you in just a minute. And then finally, there were Faraday's law and this should say Lenz's law, not Lorenz's law, but Lenz's law, Lenz'. And Faraday's law connected a changing magnetic field or changing magnetic flux to a electric potential or to a voltage, and was the basis for motors and generators. Okay, now these were done with the exception of Coulomb's law. These all of these were expressed in using integrals in Physics 202, as you'll see in a second. But we'll be using, because our goal is to get to Maxwell's equations, we'll be using differential vector calculus. So vector calculus with derivatives. We'll use the integrals, but we'll also express it in terms of the differential vector calculus in Physics 350. Okay. All right, so some important equations. Recognize this one. This is Coulomb's law. The electric force is a constant times the product of two charges over the distance squared times a unit vector pointing from one to the other. And this is the electric field, which is similar. It's the same Coulomb's constant times the source of the electric field over the distance from the charge squared times the unit vector to the point where you're trying to find the electric field. Okay, this is electric flux, written as, this is called a surface integral, okay, which we'll be talking about in a couple classes. A surface integral basically means to take a electric or a vector field and integrate it over the varying surface. Okay, so, and we'll talk about how that happens exactly. But that is defined as the flux through the surface, phi sub e, is the surface integral of the electric field. And then this equation here says the electric flux is equal to the amount of charge enclosed over this constant, epsilon naught. It's called the permittivity of free space, but we'll just call it epsilon naught. Okay, so this is Gauss's law right here. Another important equation is the equation for the electric potential, or the voltage. The change in the voltage between points A and B is minus the integral from A to B of the electric field dotted with the distance in moving from A to B. Okay, so essentially the electric potential, the difference in the electric potential, has to do with how the electric field varies in space between 2 points, A and B. And essentially, it's the electric field times distance with a dot product thrown in to count more sizably electric fields which line up with the distance that they're following. Okay, now a couple of specialized formulas. This is the magnetic field of a long straight wire. It's equal to the other important constant, mu naught, which is the permeability of free space, we'll just call it mu naught, times the current over the 2 pi times the radius, and that is the magnetic field due to a long straight wire. Okay, so it's a magnetic field due to a long straight wire. Remember, the magnetic field due to a long straight wire curls around the wire in concentric circles. This is the Lorentz force equation. If there's just an electric field, the force is Q times the electric field. But if there is a magnetic field, if there's no electric field present, then the magnetic force is the charge times V cross product with B. And I'll be reminding you about the cross product in just a minute. So it's proportional to the charge, proportional to the speed the charge is moving, and proportional to the strength of the magnetic field, the magnetic force. This little baby here is the Biot-Savart law, okay, which we'll be reviewing later in the class. It's a rather a bit of a complex equation, but it basically says that if you have a little piece of current, I, with direction dl, and you want to understand or you want to calculate what the contribution of that current is to the magnetic field at a distance r away from that piece of current, you take the current times that differential length, cross product with the unit vector towards that unit length over 4 pi r squared. Okay, so notice over 4 pi r squared, kind of like Coulomb's law up here over r squared. So that's the Biot-Savart law, and we'll be using that later in the class. Just want to remind you that you have covered it, although you might not remember it right off the bat. This is Ampere's line integral law, or just Ampere's law, which says that the line integral of the magnetic field dot around a circle or around some closed curve is equal to this constant mu naught times the amount of current enclosed. Okay, so if no current is enclosed by a circulating loop, then the line integral of the magnetic field would be 0. Okay, if current is enclosed, the line integral will not be 0. Finally, we have, or not quite finally, but we have the magnetic flux, which just like the electric flux, it's the integral of B dot dA. The surface integral of the the surface integral of the magnetic field over the over a closed curve, sorry, a closed surface, and that's called the flux. And this is a little bit hard to read, but it says the magnetic flux phi sub b, flux phi sub b, is equal to 0. And that's kind of surprising because the electric flux was equal to the charge enclosed divided by this constant. Magnetic flux being 0 is a reflection of the fact that there are no isolated magnetic charges. In other words, magnets come with a north and a south pole, so they always come in two parts with a north and a south pole, and there's no single north pole or no single south pole. And because of that, there's no magnetic charge, no isolated magnetic charge, and this magnetic flux through a surface is always 0. And then finally we have Faraday's law, which says that the electromotive force, which is the voltage around a closed curve, okay, the voltage around a closed curve, like up here, integral of E dot dl, is equal to minus the rate of change of the magnetic flux with respect to time, okay? So if we have a circle or a loop, and the magnetic field increases in that loop, magnetic flux through that loop will change, and that will induce a voltage around the loop. And that process is known as electromagnetic induction. Okay, so those were some of the important equations. And we'll be getting some practice with those equations as we go through the course and in class, in our first class. So let's do a vector algebra roundup. This is section 1.1 of the textbook. So first, what's a vector? A vector is a magnitude and a direction. It's true in 2 or 3 dimensional space, but in general, a vector is mathematically is just an ordered list of numbers. Okay, so we can have a 2, 3, 4, 5, 6, 7 in principal numbers listed, and those would be vectors. We're going to be dealing with 2 and 3 dimensional vectors since we're physicists or studying physics. So adding vectors, remember to add vectors, we just add the respective components of the vectors. We can either add geometrically or add add by component. Adding vectors is commutative, meaning if you add vector A to vector B, that's the same as adding vector B to vector A. And adding vectors is also associative, meaning if you add vector A and B first and then add vector C, that's the same as adding A to the sum of B plus C. So that vectors follow the same commutative and associative laws as regular numbers. Multiplying a vector by a scalar essentially extends or contracts the vector by the amount of the scalar. So we can express this by saying that the scalar, which is this little a, times the vector A plus the vector B would be equal to what? You can think about this for a second. What would that be equal to? Okay. So it turns out it's just equal to the scalar A times the vector, capital A, plus the scalar A times the vector, capital B. Okay, so this scalar A, little a, just distributes through the two vectors. And this is how we multiply vectors by scalars. All right, now let's go on to multiplying vectors. There's two ways that we can multiply vectors. There's the dot product, which produces a number, or rather as a scalar, technically speaking. And here are two vectors, A and B, separated by an angle theta. The dot product, this is A dot B, not A minus B, can be written in two ways. It can be written as the magnitude of A times the magnitude of B times the cosine of the angle, this angle between the two. Or it can be written in terms of the components of A and B. A and B each have components, X component, Y component, and Z component, and the dot product of A and B is equal to the sum of the product of the X components plus the product of the Y components plus the product of the Z components. Okay, so these are two alternate forms of the dot product, and it's possible to prove that they're equivalent, but we're not going to worry about that proof in this course. So let's ask one question. If, according to this definition, if A is parallel to B, what would A dot B equal to? Okay, so if A is parallel to B, what would A dot B equal to? Okay, so I'll let you think about that for a second. So it has to do with the angle. The most convenient way to think about it is the angle involved in the dot product. Okay, so I'll give you that just a little bit more time. All right, so so the answer is if A is parallel to B, the angle between A and B is 0, since the two of them are parallel, and the cosine of 0 degrees is 1. So we have the dot product would just be equal to the length of A, the magnitude of A times the magnitude of B. So A dot B would just be equal to the magnitude of A times the magnitude of B in that case. What about the case if A is perpendicular to B? What would then A dot B equal in that case? Okay, so I'll let you think about that for a second. All right, so again, the key here is using the angle definition. If two vectors are perpendicular, the angle between them is going to be 90 degrees. And so the cosine of 90 degrees, if you check, or if you just remember, hopefully, but if you check your calculator, cosine of 90 degrees is 0. So A dot B would just be equal to 0, since multiplying by 0 would give nothing. And so the dot product A dot B being equal to 0 is a nice way to express the fact or the condition that two vectors are perpendicular to each other. All right, so that's the dot product. Let's talk about the cross product. The cross product, rather than producing a number, produces another vector. And okay, so this is a somewhat big equation all at once, but the cross product of A and B is equal to the magnitude of A times the magnitude of B times the sine of the angle between A and B, rather than the cosine, as in the case of the dot product, times a unit normal vector, which is determined by the right-hand rule applied to A and B, okay? Because there has to be a vector here because the cross product produces a vector. Okay, so you probably have memory of this matrix here, or determinant. So the way that we calculate the cross product is we set up a determinant where the unit vectors x, y, and z are in the top row, the components of A are in the middle row, and the components of B are in the lower row. And if you remember the rule for taking determinants, I'll just sketch it out fairly briefly. We take the first component here, and then we take the determinant of the this submatrix over here, the rest of the matrix. So this would be x times AYBZ minus BYAZ. And then when we come to this second element, the rules for determinants tell us that we have to switch the sign. So we would have minus y hat times AXBZ minus AZBX. And then for z, we would have AXBY minus BX, AXBY minus AYBX, just as we did for the x hat component. Okay? So that's how we take cross products. And here's an example of both. So let's just take two vectors here. Vector A is the vector 1, 2, 3. Vector B is the vector 2, 4, 6. To take the dot product, the easiest way to do it depends on what information you're given with the dot product, but here we're given the components. So the easiest way to do it is just to multiply the components. So it'd be the x component of A times the x component of B plus the x component of, the y component of A times the y component of B plus the z component of A times the z component of B. And if you add all that up, we have 2 plus 8 plus 18, we get 28. So that's taking the dot product of these two. Taking the cross product, okay, using this definition here for the cross product, I'm not going to go through in gory detail here, but you can pause and verify that what I've written here obeys this rule for the cross product. We have x hat times 2 times 6 minus 4 times 3, so 12 minus 12, minus y hat times 1 times 6 minus 3 times 2, 3 times 2, plus z hat times 1 times 4 minus 2 times 2. Okay? And each of these is 12 minus 12, 6 minus 6, 4 minus 2. Each of those is 0. So therefore, A cross B in this case would be 0. Why would that make sense? Why would it make sense that A cross B would be equal to 0? Well, if you think about the alternate definition for A cross B, it's equal to the magnitude of A times the magnitude of B times the sine of the angle between A and B. These two vectors, 1, 2, 3, and 2, 4, 6, are parallel since they're multiples of each other. And parallel vectors have an angle of 0 between them. So the angle here would be 0, and the sine of 0, as you probably remember, is 0. So that this part of the formula shows that A cross B here, we could have gotten directly that A cross B would be equal to 0. Okay, just a little bit more of vector algebra roundup. There's something called the triple product, okay, which combines the vector and the dot product. So this is a triple of vectors, A, B, and C, okay, drawn at angles to each other. The angle between B and C here is theta 1. The angle between the vertical direction and the A is theta 2. So it turns out that this form, the dot product of A with B cross C is related to the volume of the parallelogram. So the parallelogram, which is formed by these three vectors. Okay, so this would be the base of the parallelogram, and the height of the parallelogram would be the vector A. So why is that? Well, B cross C, by our definition, the length of B cross C is the length of B times the length of C times the sine of the angle between them. If you work out geometrically, excuse me, C times the sine of that angle is this little height. So we have the base here times the height of this I guess it's a rhombus. Is that right? Anyway, parallelogram, two-dimensional parallelogram. So that would be the area. So that gives the area of this parallelogram, defined by B and C. And then to find the volume, we would need to multiply that, scale that parallelogram by the height to which it extends. Now, it doesn't extend quite as far as the vector A, because A points at an angle. So how far does it extend? Well, it extends the component of A up to the component of A, which is perpendicular to B cross C. So it extends by this amount here. Extends by this amount here, not the full amount A. And that parallel amount is given by the A times cosine of theta 2. So we would have A times cosine of theta 2, which would be the height, and B cross C, which we just showed, is the area of the parallelogram. But A type vector, the length of a vector times the length of a second vector times the cosine of the angle between the two of them gives the dot product. So we have A dot B cross C. So that's the area of the parallelogram times the height, A cosine theta 2. So A dot B cross C is called the triple product, or sometimes the scalar triple product, and gives us this volume here. And it's possible to show, we picked A as our height here, but we could have picked C or B as our height. It's possible to show that A dot B cross C is equal to, if we had picked B as our height, B dot C cross A, or C dot A cross B if we had picked C as functioning as our height. So all these three equivalent are equal to the volume of the parallelogram, the three-dimensional parallelogram defined by the A, B, and C vectors. And last part of the vector algebra roundup is the vector triple product. This one doesn't have a geometric interpretation, but we will use it from time to time when we're solving problems algebraically. It says that the cross product of A with B cross C is equal to B times the dot product of A and C minus C times the dot product of A and B. And sometimes this is known as the back cab rule, because we have back BAC minus CAB. So you might remember the back cab rule, or you always be able to look it up in the front of your textbook. And finally, the position vector, we'll be using that in future classes and relationships. This should be fairly straightforward, hopefully, but the position vector R of a point in space would just be equal to its x-coordinate times x hat plus its y coordinate times y hat plus its z coordinate times z hat. So then what would the length of r be equal to? The length of r would be equal to the square root of the dot product of r with itself, the square root of magnitude of r squared, which is the dot product of r with itself. And if we look at that dot product of r with itself, we can, if you think about it, you find that that's just x squared plus y squared plus z squared. Okay, because when you take the dot product of r with itself, the cross terms x and y, x dot y is 0, x dot z is 0. So you just wind up with x hat dotted with x hat, which is x squared, and so forth for y and z. So, which is long-winded way of saying that the magnitude of the position vector is the square root of x squared plus y squared plus z squared, which you probably realized. Oops, sorry about that. And that's all for this lecture. And I just want to remind you to come to class ready to work in teams on problems based on this. I won't be doing any aside from individual explanations of things which didn't make sense from this lecture. I won't be doing any lecturing. We'll come in and just be working on a series of problems together to try to get a good handle on this material. Okay, thanks, and see you in the first class.